Welcome to lecture number 29. So, we are almost 2/3 done of this course, only 1/3 is remaining. So, there are 40 lectures in this course, 28 are almost done, only about 12 lectures are remaining, including today's lecture. And I hope you must be enjoying the lectures, because in the last about 15 lectures we have been discussing about machine learning as well as deep learning algorithms. So, you have gotten good sense of both the different types of algorithms and especially the algorithms which will be widely used in material science, and that is what I am focusing. You know, there is no end to discuss about different types of these machine and deep learning algorithms, but we like to limit ourselves to the specific algorithms for material science engineering applications. And in addition, we have also a time constraint, right? I cannot keep on discussing on different kinds of algorithms and eat up all the time. So, the next 12 lectures, what we are going to do is very specifically, first we are going to discuss about materials at different length scale, and today we will start about that lecture, and I will explain why we need to know the materials at different length scale, and what is its connection with the machine learning and deep learning, that we will discuss later part. And once that is done, another 3 to 4 lectures, then we will come back to advanced deep learning techniques, where I will discuss some of the techniques which I have left behind for the last 3-4 lectures for NMARC for deep learning, and especially we will discuss about techniques which are really advanced and useful for material science engineering applications. And that is the second thing after the materials at different length scale. And the last part, about 3 to 4 lectures, we will spend on material informatics, how we can use data science in materials engineering modeling. And we know that we have a lot of data in various kinds of materials. We will talk about it, what is the ways and means to do that. So, that is so this in a nutshell for the next 12 lectures we will be spending. So, let us do first, although we are going to discuss materials design at different length scale, we start today the part 1, and there will be subsequently 4 lectures including today's one for this one, but first let us do some recap. We have discussed about various kinds of deep learning models, and the last lecture we talked about mostly the unsupervised learning deep learning models, and this chart is very common to you now because I have been showing to you. So, we have 3 different types of deep learning models. First one is supervised models. For that we have discussed about multi-layer perceptron type models, convolution network neural networks, then RNN, or what is called recurrent neural networks. As a part of we have discussed about LSTM and GRU, right? And then we discussed about generative artificial neural network, autoencoders, SOM, and some part of DBN. So, what is left behind is basically DTL, DRL, and some combinations of these neural networks, which will be hybrid, what is known as a hybrid deep neural network models. So, this is what is going to be talking about in the advanced deep learning techniques. And we also discussed something about how we can do both model based as well as model free modeling. So, this is very interesting actually. These are the new insights which is coming for the last 3-4 years. So, we will touch upon some of these aspects on that. And as I told you, deep learning requires a lot of data as compared to machine learning. So, if you want to embark on applying or using deep learning models, what you should do is basically you should try and use large amount of data. You should have it with you, otherwise these models will not be very effective. If you do not have, suppose you are working on advanced materials for which data are limited, then you are going to use machine learning mostly, because machine learning algorithms are good as far as the accuracy is concerned for less data sets, right, lower amount of data. But deep learning models will not work well if you have less amount of data. But in these connections there are models for deep learning which can be used for less amount of data. We will talk about it, very interesting models in the advanced deep learning sections. So, what have we done? We have done CNN, ConvNet, RNN, and we have done also generative adversarial network, that is part of the last lecture, autoencoders, then self organized maps, SOM, and also we will talk about this aspect DTL, DRL and all these things as a part of our advanced DIP, advanced DLL. Now, I will show you how these techniques are useful. So, formally we start discussing in the last lecture about some of the unsupervised learning in DNN, and it is very important aspects of DNN, and it is in fact people say it is very important, not only it is an intriguing area of machine learning or deep learning, because it can reveal hidden structures or hidden patterns in data without any level samples. Remember, in supervised learning you need to have both input variables as well as level data, that is input and output. But in unsupervised you do not have that kind of luxury of having both the input as well as the level data. So, once you do not have level data, what you do? You need to find only hidden patterns or hidden structures, and we have discussed about this aspect for clustering and many other models for machine learning, right. So, that is the key things in unsupervised learning in deep learning networks. So, these techniques are typically you will be used for to find higher order correlation properties or features for pattern analysis or synthesis. Sometimes it can be also used for statistical distributions of visible data and their associate classes, that is also possible. But mostly they are used for correlation, higher order correlation properties of features or for pattern analysis. Okay, that is the key aspects of any kind of unsupervised learning. And therefore, it is an effective tool for anomaly identification, dimensionality reductions and as well as clustering. Remember that clustering is not only part of your machine learning, clustering can be used in deep learning also, but important aspect to have sufficient data, then only your interpretation will be good, because it provides insightful information, it can enhance the decision making process, that is what it is. So, without sufficient data, this DNN for unsupervised model, unsupervised learning is not going to work. And you know that an unsupervised learning network may be under guidance of features or may not be. For deep learning it is not under guidance of any features, and it is used for all kinds of things, I talked about it. So, the key idea is what? During learning, precise supervised informations of target variable levels are not an importance. So, you do not need supervisory informations, you did not have target levels that we have talked about it. So, what as a result of this we find correlation of input data or features or even data representation. Many cases you need to represent data properly, and that is what. So, all the algorithms will be based on this idea or these concepts of finding patterns in all level data. So, what are the different components? That is why very simple. First one is obviously you need to have an encoder decoder type of things. We talked about it, autoencoders, let me explain to end. So, encoder is going to encode the data, and or rather what it will do, it will reduce the dimensionality of the data, and then it will place the data in a latent space. This is the immediate representative data created by this encoder is placed in a space called a latent space, and it contains usually features which will capture important aspects about this data or structure of data. It will not contain all features, it will contain only important aspects of the features of about the structure of data. That is the key thing about encoders. Encoder does it very nicely, and decoder will simply decode that data after it is taken from latent space. So, you also need to have some training algorithms. Most of training algorithms are neural network based obviously, but you can also use stochastic gradient descent methods also. We have not discussed about it. If I get time for the advanced deep learning method, I will talk about it. Gradient descent is very simple, but what is stochastic, that is something requires discussions. So, how do you find out the error? Basically you find out error by loss functions. We have been learning these aspects, and it will quantify basically how well the model can understand the data. That is what is the loss function. These are the 4 components of any unsupervised learning technique: encoder, decoder, latent space, training algorithms and loss function. So, now we are talking about first important model is a autoencoder. What is autoencoder? Well, it is nothing but a very important technique. It is a very popular unsupervised learning technique, and it is used to learn only data representation. And typically these autoencoders are used to work with high dimensional data. High dimensional data means data which have many features or many dimensions, and this dimensional reduction is the most important thing which is to be done by autoencoder. So, dimensional reduction explain how a set of data is represented. So, you have a encoder, you have a decoder, you have a lateral space. So, encoder basically code, encoder or decoder are the encoder, code and decoder, the three parts. They are the main important space for this kind of things, and encoder actually compresses the data or compresses the input data and generates the code basically, and which is taken by the decoder, and subsequently it is used to reconstruct the input. That is what is the most important aspects. So, it has a encoder, it has a code and it has a decoder. So, encoder basically compresses the data and generate a code, and by compression we mean it basically reduce the dimensionality of the data, and that is why it does a lot of important dimensional reductions, and then once it is done it will be stored in latent space, and that from the latent space data will be taken by the decoder to reconstruct the data again. That is the main aspects of the or any autoencoder. As you can see here, if a input line, this is basically sparse encoder, example of that. There are different types of encoders. So, it is sparsely parallelized, the sparsity is parallelized on the coding layer as a part of training requirement. What is the meaning of this? Let us say these are the input layers, okay, and then you have hidden layers. We do not use all the units of the hidden layer, we use some of the units, like here 1, 2, 3, 4 units are used out of 9 units. So, that is why it is called, this I call active units. So, by that way you have a sparsity penalized aspects, right. We are not using all the active units from the hidden layer. So, we are doing that, and this is the way you can actually compress the data a lot. So, it is at a pass of training requirement actually. So, it may have more hidden units than the input, but only a small number of hidden units are permitted to be active at a certain point of time. That is why it is called a pass model. And as I have written in the last lecture, encoder actually compresses the data and generate a code, and this is then placed in a latent space which is nothing but a stored space, and then decoder actually takes the data and effective reconstruction of data is possible with the decoder. So, what are the important characteristics? First is that it reduces the dimensionality of data. Most of the cases you see, because deep learning requires a lot of data, and there will be huge amount of data will be present, and the dimensionality will be massive, and it may not be possible to handle them in a nice manner. If you can handle it using a large CPU or GPU whatever, then is fine, but most of the cases it may not be possible to do that, and that is why you need to reduce the dimensionality. And second reason is that many cases some of the features will not have an important role on the model. So, that those features can be again removed, and that is how we can reduce the dimensionality also, and it can learn the hidden features also. That is the major thing. Third thing it can do is the denoise the data, remove a lot of noise from the data. These are the things which autoencoder can do, and these are very important for data preprocessing many times. You will see data encoder, autoencoder can be used as a data preprocessing technique also. That is one of the aspects we do that. So, what is denoising encoder? Basically, it is a variant of the basic autoencoder, and it attempts to improve representation by altering the reconstruction criteria. Basically, what it does, it reduces the risk of learning the identity functions. So, in a nutshell, if I have to tell in a very simple manner, it receives a corrupted data as an input, and then it is trained to recover the original undistorted input as output. How does it do it? Does by minimizing the average reconstruction errors. That is why it is called denoising, it removes the noise. So, key points is receive a corrupted data as input, and then it is trained basically to recover the original undistorted data. It is very widely used in telecom sectors, okay, and then it does produce output by minimizing this average reconstruction error. So, this DAE or denoising autoencoders can be considered as very powerful filters. Remember, they are very powerful filters and can be utilized for automatic preprocessing of data. So, we are actually learning a lot of techniques for preprocessing data, which I will discuss in some of the part of lecture also earlier later, but this can be used as a preprocessing technique for the data. Then you can also have contrastive autoencoders. Here the idea is to make autoencoders robust to small changes in training data sets. If you have a large training data set and if you are changing the training data set by small, will it affect your training of the model. So that is what can be ensured by using contractive autoencoders. So and it is an objective functions which includes explicit regularizer, and what does the regularizer does? It that forces the model to learn and the training input is reduced. Okay. So that means what? Encoding that is robust to small changes in the input values. So it will be forced to learn, and it will then as a result what will happen? The learned representation will have a lot of sensitivity. Small change cannot affect the training, that is what it is. So if there is a small aberration, the training data can it affect your learning. The last one we talked about is what is called variational and autoencoders. This is a little bit complex. It has a fundamentally unique property that distinguishes it from any classical autoencoders because it is effective for unsupervised learning. What does it do? It maps the input into a latent vector and this input data into parameters of a probability distribution. That is what it does. So it can take the input data and do the feature engineering and all these aspects and then map into a parameters of a probability distributions such as mean variance of Gaussian distributions. So that is also required many times for data preprocessing. So as you can see, autoencoder can be used more for data preprocessing or to learning. In fact, like the contractive autoencoders can be used for learning purposes also. So in a nutshell, this is a neural network or deep neural network that learns how to compress or decompress data. That is what basically autoencoder does, but there are different things. It can be trained to reconstruct the input data from a compressed representation. It can also be used to map input data to lower dimensional representation, which can be done by reconstructions, and they are feed forward neural network by the way with encoder and decoder. So it can be widely used for image reconstructions, image compressions, dimensional reductions, removing the noises, all kinds of things. The last thing which we talked about in the last lecture is generative adversarial network. This is little bit different. This type of network whose architecture is different from the earlier ones. So it is like more like a generative modeling to create new possible samples on demand. What is it? It contains two neural networks. One is generator G, you can see here, which will create a lot of new data having properties similar to the original input data, but who is going to check that the data which is generated by G is actually following the trend of the input. That is why you need to have a discriminator D, as you can see here D, and this D predicts the likelihood of the subsequent sample being drawn from the actual data rather than data provided by the generator. Okay. So it is going to check that whether data generated by the generator is likely to be that of actual data which you have used. Okay. So that is why it can be used for image generation, style transfer, data augmentations. Remember, you will use many modeling and material science modeling to discover new materials, and you may not have sufficient data, and you will find you need to generate data. So when you generate data, how do you ensure the generated data and whatever input you have, they are going to be same type of data, or generated data is highly likely to be of sample data which you are going to use directly from experiments or calculations. So that can be only be checked by using GAN or generative adversarial network. So it is basically essential tool for any unsupervised deep neural network, and it has the ability to capture complex data distributions without any need of any leveled inputs, but it requires a lot of learning, and that is why it is vulnerable to mode collapse. And it can actually, why it is so? Because generator can concentrate on small number of data patterns. It obviously depends on how good your generator is. If generator concentrates on small number of data patterns, then it will create biased data. That is not the required thing, right? You need to create data which is likely to be of a original data. So it has completely changed the field of machine learning. Why? Because it is one of the techniques which can allow you to generate data, which is the same likelihood of your original data. So therefore, whenever you have a problem of less data availability from experiments or calculations, this guy can help you to design some kind of a data generator along with discriminator to make sure whatever data you generate can be used for a deep learning model. Well, self-organizing map or SOM, or what is called Conan map, is basically creating low dimensional representation of high dimensional data, and that is also a part of a data preprocessing, but it maintains the topological structure of the data. Topological structure means what? The tuple structure means top to bottom how the data are connected, that it maintains. And therefore, dimension reduction algorithm, it is nothing but a dimension strategy. It is commonly used for all kinds of clustering things. And it adapts to technological form of a data sets by typically moving this neuron to closer to the data points, so that we can visualize the enormous data sets and find probable clusters. And this is commonly employed for competitive learning, and here to that we use the neighborhood functions to retain the input space topological features. So, idea is basically you have to repeatedly move the neuron closer to the data points, then only you can visualize these enormous data sets, and possible to do lot of dimensional reduction by this technique. So, that is the thing which you learned in the last lecture. It is almost something which you should remember, but some of these techniques which will come back again when we talk about data preprocessing as a part of advanced deep learning techniques. So, now let us talk about material design at different length scales. What are these? Well, I would like to first go back to the board on why we need to do that. Okay, material design at different length scale is very important. Why? Because we have seen that from the structure of materials, the material structure starts with atom. Let us talk about electrons. If we start with the atom, and what is the dimension of the atom? If I considered any carbon atom, let us say carbon atom, its size is almost 0.89 angstrom. That means 0.89 10 to the power minus 10 meter, correct. So, if I then build with the carbon atom diamond cubic structure, diamond structure, okay. Diamond has FCC based structure, but it has also tetrahedral coordination, carbon has a tetrahedral coordination. So, in a FCC structure you have a lot of voids, so those voids are filled up. So, I am first going to draw these corner atoms, then some of the FCC atoms, not all. Okay. Let us do that. So, now you can see clearly I have a tetrahedron, right, created. Am I clear? So, you can also place a carbon atom here. So, that is what it is. This carbon atom is tetrahedrally coordinated with all the 4 carbon atoms. So, this kind of tetrahedra is there all throughout. So, that is why you have basically 4 atoms in FCC unit cell, you can see that. So, there are 6 faces. So, I have done 1, 2, 3, 4, then I should do one more here, central space. Let us do by this as a field circles, and then one here backspace, this backspace. Okay. So, then this one is also part of this. So, you can see there are 6 atoms, right. So, virtually speaking it has 4 atoms from the FCC and then 4 atoms from the inside. That is what it is. So, one atom of carbon has a size of almost 1 angstrom or 10 to the minus 9 meter. Now, diamond unit cell is, I think A unit cell diameter is about 4.2 angstrom, I am not sure, but something like that. So, close to 4 angstrom, let us take. So, you can see here this is 1.9 angstrom, we go to 4 angstrom, that is correct. So, that is what is the length scale change, you can see 1 order of magnitude change. Now, we can build, what do you do? Normally diamond is used as jewelry, other than that industrial application use a diamond as a coating, right. If you clearly see, diamond is also used as a coating, because it is a very hard material. Diamond is the hardest among all the materials. So, diamond can be used as a coating on the cutting tools. So, coatings will be of the order of thickness of let us say about 10 to 15 micron. So, if I have a cutting tool inserts like this, okay, this kind of inserts again like that, you deposit diamond here, diamond on the faces. Okay. You may have seen some cutting tool blades. So, thickness of these diamond coatings, diamond coating will be of the order of microns. And what is a micron? So, that means 10 into 15 into 10 to the minus 6 meter, right, either 10 to 15, 10 to the power minus 6 or 15 to 10 to the minus Okay. So, let us talk about like that will be very easy, that will be confusing meter, right. So, you can clearly see from minus 10 meter to you have gone up to minus 6 meters or in fact minus 5 meters. Okay. So, now, so you can even build larger. So, the one with this tool, this is called a tool tip. These tool tips are very large, they are of millimeter size. Okay. Tools actually why millimeter, centimeter, I think about centimeters, couple of centimeters, 2 to 5 centimeter, let us say. So, 1 centimeter is 10 to the power minus 3 meter, correct. So, we could see that from 10 to the power minus 10 we have reached out 10 to the minus 3. So, length scale changes do take place when you manufacture something, when you produce a component. That is a very typical aspects of any application of a material. So, we start with atoms, then we go to the component. Okay. So, this is atomic and this is component. So, hence from here to there this order of magnitude length scale change. So, 10 to the power minus 10 meter to 10 to the minus 3 meter. It can be even bigger. If I talk about silicon, it will be much bigger, right. Silicon is solar cells and that can be of the order of meters, right. So, forget about centimeters. So, this is the typical length scale change happens. So, if you want to model at all length scale machine learning models, you should know how things are going to change based on this models. Okay, that is the key aspects of this kind of problems in AI/ML, because if you want to model at the atomic dimensions, your model must be different than if you want to use a model at component level dimensions. So, how to take care of that? That is a part of this discussion. Another thing which you will probably must have already understood, that the calculations which can be used at the atomic level. Okay, calculation means whether we can understand how the diamond structure forms, why not something else forms actually. So, why not hexagonal crystal structure of diamond, why only cubic type of crystal structure of diamond forms, what kind of things stabilizes. So, those calculations can generate a lot of data, huge amount of data, and that data can be used for machine learning. So, there are two pronged purposes. One is obviously the two main purposes. One is obviously data generation, as I told you, data generation by computation, modeling. That is number one. Number two is how to model materials at this different length scale. So, we will discuss more about this in the second part of the lecture, but basic concept I already discussed about you, that from atomic level to the component level there is a dimensionality change, or basically orders of magnitude change happen. So, how to take care of that? So, I am not talking about subatomic will be electrons, right. So, there even dimension can be reduced further. So, let us stop here, we will come back to it in the next part of the lecture.